Hello everyone, my name is Hanyu Cheng, and I'm from Tyndall Institute in China and I visited the University of Sheffield in UK now. And today I want to talk about constraining pressure-based DDE with the latest cosmological data. It's according to, based on my recent paper, the archive number shows here. First, I want to briefly introduce what is DAC-Eng. And I think everyone knows DAC-Eng. It's like the first evidence for DAC-Eng is from this, like in 1998, we used type 1 supernovae, discover like universe is accelerated, expanded, and these things won the Nobel Prize. And now we know that can compose 70% of universe according to lambda CDM, and lambda corresponds to cosmological constant, and CDM corresponds to dark matter. And this lambda CDM model is called the standard model in cosmology. But this lambda CDM model is challenged by the recent DESI BO data and the DESI 5 supernovae data. Then I want to briefly introduce the datasets I used in my project. What is CMB? CMB is a snapshot for the recombination at around 1100. We know the CMB is a nearly perfect black body radiation with a temperature and entropy around 10 to -5. If you see this right panel, the first peak tells us the size of the sun horizon at recombination. And the datasets I used, including the Planck 2018 data, including high L Planck TT likelihood and low L TT only combined likelihood and low L EE only single likelihood. Besides that, I also used ACT DR6 lensing, which I use the ACT Planck baseline, which combine the Planck lensing and ACT lensing together. We call this as a CMB in total. And what is BAO? And BAO is the standard wave in the early universe. In the early universe, the temperature is really high. The photon and electron couple to each other. This since the gravity and the pressure work against each other, this plasma is like a sound wave can travel very fast. And when the temperature goes down, this electron combine with a nucleon to form neutral hydrogen. Then this sound wave frozen at recombination, and this is called the BAO. And this sound horizon scale, sound horizon is very important. We can still see it in nowadays. In the right panel, we show the histogram for the two-point correlation function of galaxy. This peak gives us the typical size for the BAO scale in nowadays. And the BAO datasets I use in my project, including SDSS and DESI DR2 datasets. The redshift range of BAO BAO is around 0.1 to 4. And I also use the type 1A supernovae datasets. Type 1A supernovae is called as standard candles in our universe because they have uniform peak luminosity, and we always use them to do distance ladder calibration, and they can work as a direct evidence for the acceleration and work as lead time probe method. We can use them to direct measure luminosity distance dl and the h0. The right panel shows different samples of supernovae. The different color correspond to different sample of supernovae, and we have more than 1,000 samples. This is plot is from Python Plus paper. And we can use a different cosmological model to fit these supernovae examples. In our project, we include Pantheon plus supernovae dataset and DESI 5 supernovae datasets, which have different number of supernovae and different redshift range. This is the recent DESI 2 result. I think most of you have known this result. They use the CPL parameterization to test the dynamical dark edge. In CPL model, the W0 is the present value of equation of state of dark edge, and WA measures how this dark edge evolves with the scale factor. And in this plot, the W0 equal to -1 and WA equal to 0. This point correspond to lambda CDM case, and different circle correspond to different datasets combination. As you can see, like here, all the datasets shows the deviation from lambda CM that adds more than 2 sigma. This is hints at dynamical dark edge, and especially for CMB plus DESI plus DESI 5 shows 4.2 sigma preference over lambda CM. And the motivation of our work is we think that besides using CPL, we can use a different method, the different parameterization way to test dynamical dark edge with the latest datasets, and to see if when we use a different datasets, when we use different parameterization way, will datasets give the similar result as CPL or the opposite result? So we consider pressure parameterization, which we didn't do the tail expansion for equation state of dark edge. We do the tail expansion for pressure P of dark edge. As you can see here, the P minus P0 corresponds to the present day pressure of dark edge, and P1, P2 is the first order expansion and second order expansion parameter. In our case, for second order expansion, we have 2 parameters, omega1 and omega2, which correspond to P1 and P2. Somebody might ask why the P0 is not a free parameter here, because P0 corresponds to the present day edge density of the dark edge, and this value could be derived from the edge density of other components, because we require the universe is flat in nowadays. So if we use this pressure parameterization, it could be considered as an independent consistent check besides for the CPL. And we use 2 different statistical methods in our project. The first one is the dead chi test. This dead chi value could convert to n sigma significance. And we also consider Bayesian evidence. This Bayesian evidence not only consider the maximum likelihood, it also consider how many parameters in your model. More parameters in your model, the Bayesian evidence would penalty your model more. And this right is a workflow for a project. We first modify the Cheng according to the pressure parameterization, and we using the different datasets and the input of these things into Cobaya to do MC running, and we get that chi-square and that rho in Z. Then I would do, here you can see the formula for the pressure parameterization is a tail expansion for the present pressure value, and we consider first order first, and then we extend it to the second order expansion. If we know this pressure formula, we can input it into continuity equation, then we can get the edge density formula for the dark edge. And here we do some reformulation to change this parameter to the dimension of this parameter. And as I said, for our first order model, we only have one free parameter here, which is omega1. And then we have the energy density and equation of state for the dark energy. In this case, the one thing we need to notice is that we have a pole in equation of state of dark energy when the denominator of equation state is equal to 0, which corresponds to the green line and the yellow line in this plot, and this corresponding to the sign changing, which means the energy density of equation of dark energy change from negative energy density to positive energy density. And for second order expansion model, we have one more parameter, omega 2. Here, we can also get the energy density formula and equation of state formula. And I want to strengthen the comprehensive of our second order model. In this plot, you can see we can our second order model include different situations for the dark energy. We have the quantization behavior corresponding to the purple line in this plot, and we have a fountain dark energy behavior corresponding to the green line in this plot, and we also have fountain crossing behavior corresponding to the blue line in this plot, and we also have a poles in equation of states corresponding to the yellow line in this plot, because like we have our second order model include different situation, and so we can just let data decide which situation is preferred by them. Besides that, I want to show that our pressure parameterization is equivalent. It can be decomposed into different components of dark energy fluid in physics. For our first model, this our dark energy is could be effectively decomposed into CC, cosmological constant, plus a fluid with equation of state equal to -4/3. And for a second order model, this dark energy could effectively decompose into CC plus 2 fluids, like with a different equation of state value. Here, if you see these two formula here, you can see when A equal to 0, this in our case, dark energy become cosmological constant in the early universe. This is different with the CPL model. And we show the result for our first order expansion result. As you can see here, if we consider CMB only, it gives a very rough estimate for a parameter. And if we add BAO data, this CMB plus BAO gives the larger H0 value and smaller omega m value, which is in the right direction to alleviate H0 and S8 tensions. But if we include the supernovae data, this value, the value of the H0 and omega m, come back to the lambda value. If you see this red line, this CMB, DESI, and DESI5 gives the strongest constraint for the parameter, and it gives the best or strongest preference for the DDE in this case. The delta chi-square is -7, and it shows more than 2 sigma deviation from lambda CDM. And if you see this plot, it tells you the same thing. If you consider CM plus BAO is in right direction to solve the tension, but if you add supernovae data, it puts this H0 and omega value back towards the Planck values. This is a second order result. You can see omega 1 is most often a negative and omega 2 a positive. This is because this omega 1 and omega 2 has a strong negative correlation. You can see in this red plot. And you can see that delta chi-square is most often negative, which means the data prefer our model more than lambda CDM. Especially for the CMB plus DESI plus DESI5 shows more than 4 sigma preference over lambda CDM. The Bayesian factor is also prefer data even though we have 2 more parameters. And we also show the reconstruction of the energy density in this plot. The blue line corresponds to the first order model, which is consistent with lambda CDM, and it's always quantizing in this case. And for the second order model, it deviates from lambda CDM. For CMB plus DESI plus DESI-5, it shows more than 2 sigma deviation, and it shows the phantom crossing behavior and non-monotonic behavior in this case. We also choose the reconstruction of the equation of state. In this case, the blue line corresponds to first order expansion model, the right line corresponding to the second order expansion model, and blue line shows the CPL result. The interesting things here is if we consider late universe, the period that can dominant the universe, our second order model should behave very similar as CPL, which both of them has phantom crossing behavior. And so this is very interesting results because we consider different different parameterization with the CPL, but we get similar results across the different datasets. This is very robust to me. And we also show W0, WA plot for first order model is consistent with lambda CDM, and it has strong degeneracy and tight constraint. For second order model, this plot is very similar to CPL case, and it shows the more than 2 sigma deviation from lambda CDM. If you compare the these different circles, you can find that DESI gives us the strongest preference for DDE than SDSS, and that's why 5 is stronger preference for DDE than PP. And we also compare our model to CPL. For our first order model, the all-dead chi-square value are worse than CPL. But if you see the data law in Z, the datasets without DESI show positive data law in Z. This means this dataset better than CPL due to 1 less parameter. And if with DESI datasets, this case is worse than CPL. And for second order model, we will see it's indistinguishable with CPL. This is our conclusion here. All in all, our second order model shows a very similar behavior as a CPL in late universe, so which is very interesting.